Okay, so that's what we did in previous work. What we're going to talk about today is irregular fractional cooperation. So in irregular fractional cooperation, once again, we have many available relays, but the key difference here is that each relay contributes a potentially different fraction of its resources to relaying. So now, we have the situation where not everybody is doing the same thing. In fact, this is potentially more fair and potentially more practical. So we don't necessarily insist as price of admission that you be willing to contribute a third of your resources, for example. We could have a device that wants to be magnanimous, that wants to share, that wants to help its fellow man, that's willing to devote its entire resources to relaying. So that's fraction 1, let's say. On the other hand, we could have devices that are not necessarily being selfish, but that have a low battery, and that are basically saying to the network, well, I want to concentrate on my own transmission, so I'm only going to transmit my own data and just a very, very small fraction of additional input to cooperation. So as probably the key example of a case in which a device would want to back off is, like I said, in the case where it has low battery. So devices would by themselves choose how much to participate. In order to analyze this scenario, we have to define something that I call an outage set. We define this very carefully in the paper, but the basic idea is this. So here I have my source, here I have my set of available relays. Each one of them, once again, is contributing a potentially different fraction. Now these guys are no longer indistinguishable. So let's say my one magnanimous relay that's contributing its entire resources is different from a collection of relays that is only contributing 1/3 of their resources, and so on. So basically, an outage set is any set, as the name implies, that causes outage. So how might this work? Let's say these 4 relays all have SNR below some threshold. I'll call that eta. If, when those 4 relays have SNR below the threshold, and the other relays have any SNR, potentially up to infinity, if the result is that communication is impossible using only the relays when we ignore the direct link, then I call that an outage set. So these 4 relays with the potentially low SNRs, I'm going to refer to as an outage set. Okay, so the outage sets obviously depend on the cooperation sequence. They depend on the exact bits that are relayed by, for one thing, they depend on the fractions that are used by the relays, and they also depend on the exact identities of the bits that you're relaying. So let's let B represent the collection of all the cooperation sequences of all the relays. So the identities of the outage set depend on that. And given B, we're going to call omega of B the smallest outage set. So out there's probably going to be one small outage set, and omega B is that set. So here's the main result of the paper. The diversity order of irregular fractional cooperation, in this case, is 1 plus the cardinality of that smallest outage set. So why is that? The world's shortest sketch of a proof. Let's just think back to the observation. So when I think back to the observation I made, if under K relay failures, if that causes an outage, then my diversity order is K plus 1. So in this case, the smallest outage set, any outage set will cause a failure. So the smallest outage set, which is omega B, causes a failure. So possibly the diversity order could be 1 plus omega B. So with some probability, there will be larger outage sets could occur, but those will have smaller diversity orders. So they're all dominated by the smallest one. So the diversity order, therefore, must be given by 1 plus the cardinality of the smallest outage set. Okay, so that's nice. If I give you B, if I give you the set of all the cooperation sequences, and you then go and analyze those to death, you will probably be able to figure out what the smallest outage set is. But that's not really a way to come up with a simple system. Basically, you have to look at all possible B's and then analyze them and find out what their outage sets are. So what we've come up with is a way to bound the size of the smallest outage set, assuming that what you're doing is you're selecting bits from the transmitted sequence from the source, independently and at random. And what we've come up with is called an erasure channel, lower bound. So what's going on here? Think back to that slide where I showed the source, and from its perspective, all the symbols that were being relayed. So all these red ones, the light red ones, are all the bits that some relay has selected. So the source doesn't really care which relay selected them, but some relay has selected them. And the blue ones are the ones that have not been selected. So the best case scenario here is that all of the selected bits have infinite SNR. And we can't really do anything about the non-selected bits. Remember, we're assuming here that the direct link is out. There's no direct link. So in the absence of a direct link, if all of the relayed bits have infinite SNR and all of the unrelayed bits have 0 SNR, effectively what this is an erasure channel. So what does this mean? Basically what we're going to do is we're going to put an error-correcting code on top of that in order to recover the erasures. So for an error-correcting code in an epsilon erasure channel, what we're going to do is we're going to let this quantity, PC of epsilon, represent the error rate after decoding. So this is, if we say that P cell represents the probability that any particular bit is selected by any relay, then that is in some sense related to erasure probability. Then what we have is the probability of error in the system is lower bounded by PC, if that actually should be 1 minus P cell. 1 minus P cell is the erasure rate in this channel. So why is this lower bounded? Well, I said this is the best case scenario. Again, substitute 1 minus P cell in there. I apologize for the error. But the SNRs of the relay will not necessarily be infinite. And in practice, they will be less than that. So therefore, the probability of erasure, the probability of error in this channel must be greater than that. Furthermore, we're going to assume that this error-correcting code has a threshold called delta, such that PC of epsilon is equal to 0, so long as the erasure probability is that should be less than or equal to epsilon is less than or equal to delta. I prepared these slides last night, so please excuse the typos. Let's let H represent a subset of the available relays such that at least delta n bits are relayed. So what does that mean? What that means is that the size of the smallest outer set is less than or equal to the minimum of R minus the cardinality of that subset. So if at least delta n bits are relayed, what that means is that the code is below the threshold, so therefore the code will decode. However, if the code is beyond the threshold, the code will not decode. So the very short sketch of the proof of this theorem is that the complement of H must be an outage set, because if I don't select enough relays, if I don't have enough relays that are participating, then I need at least some finite SNR on the other relays, so all of the remaining relays must constitute an outage set. However, it's a bound, it's not an equality, because the true outage set could be smaller than that, because the SNRs are not necessarily infinite. So this is why we call this erasure channel lower bound. A corollary to this is that because the diversity order is 1 plus the cardinality of omega b, the diversity order of